Actually, there are more and more new papers on battery technologies, hydrogen production, and various things that are still in carbon capture, for example, or improved solar PV cells, etc. They're all experimental stages which have a long way to go in terms of technological readiness level, or TRL as they are referred to, and especially in terms of scalability. But I'm just choosing a few here and there based on my own personal subjective judgment to report a few of them, just to give you a sense of how things are moving. As I said, it's better to be cautiously optimistic about the future in the face of all these horrendous news about climate change than to feel anxious and hopeless and helpless, right? So this paper, obviously, again, not really my area of expertise at all. I'll just read a few things and we'll try to understand. And if you're interested, obviously, you can follow up with the whole paper and the references they provide, which are always very useful. Solid air hydrogen liquefaction, the missing link of hydrogen economy. What do they mean? Oops, so I don't know why I got... Okay, so let me increase the brightness. Oh, that's sound. Okay, that's the brightness. The most challenging aspect of developing a green hydrogen economy is long-distance oceanic transportation. Hydrogen liquefaction is a transportation alternative. Energy density in terms of any fuel is important. Hydrogen by itself as a gas is not very highly dense in energy per kilogram, let's say, but if you liquefy it, then it has much more ways of transporting large amounts of energy. So the cost and energy consumption for liquefaction is currently prohibitively high, creating a major barrier to hydrogen supply chains. This paper proposes using solid nitrogen or oxygen as a medium for recycling cold energy across the hydrogen liquefaction supply chain. That's where the solid air liquefaction title comes from. When a liquid hydrogen carrier reaches its destination, the regasification process of hydrogen produces solid nitrogen or oxygen. The solid nitrogen or oxygen is then transported to the LH2 or the liquid hydrogen carrier back to the hydrogen liquefaction facility and used to reduce the energy consumption, cooling gaseous hydrogen. Gee. Okay, sorry about that. As a result, the energy required to liquefy hydrogen sorry. As a result, the energy required to liquefy hydrogen can be reduced by 25.4% using N2 and 27.3% using O2. Solid air hydrogen liquefaction, SAHL as an acronym they use throughout the paper, can be the missing link for implementing a global hydrogen economy. What are the highlights? According to them, the energy required to liquefy hydrogen reduces by 25.4% with N2 and 27.3% with O2. Solid O2 is a better hydrogen liquefaction energy carrier than solid N2. Solid N2 is selected as the energy carrier due to the risk of explosion using O2. So you have to also worry about the risks. The solid N2 occupies 44.5% of the liquid H2 tank volume. So almost 50% is taken by nitrogen, which obviously will be removed, so you're only transporting 50% H2 liquid, but that's much more than carrying gas, hydrogen as gas, right? So solid air hydrogen liquefaction process description. I'm not going to go through the whole process, but here is H2 liquefaction. So gaseous H2 is converted to liquid H2, so gas N2 or O2. You can see the temperatures are not tremendously cold in terms of energy requirements. 300 Kelvin. So solid N2 or O2 is fed at 20 K, so that's a lot of cooling there. And there's a refrigeration cycle involved, which is required for liquefying H2. And there is cheap energy region where you want to bring green H2 and then take N2 or O2 out, and you have liquid H2 ship that is transporting it, let's say expensive energy region where green H2 is liquid H2 is stored and green H2 is taken out when to be piped, and there is air in which then carries the solid N2 and O2 on the ship back to where cheap energy region for green H2 exists. So this is H2 regasification happening here. You have again liquid H2 at 20K and gas H2 coming out 300K, solid N2 or O2 at 20K coming out with air going in at 300K, and again there is a refrigeration cycle. Obviously, I'm being very brief and not at all detailed about the processes, the pros and cons of doing it this way, but we're just taking the paper at its face value as just a report on some new ideas here on transporting H2 as opposed to producing H2. We have talked about producing H2 before, and we have talked about natural hydrogen produced on Earth, and I'm adding another podcast to that in terms of new investments in the US to tap into those natural sources of H2. Solid N2 or O2 production process to produce 99.99% pure hydrogen, and B is hydrogen cooling energy recovery during H2 liquefaction process. So you have various things going on here. H2 gas at 45 to 80K going in with solid N2 and O2 at 20K, and you have liquid hydrogen being produced at 20K, and you have various other temperature and pure H2 at 99.9% in liquid form, I think. Okay, so B is here hydrogen cooling energy recovery. So you have energy that is spent for cooling, and then you can recover it with H2 and liquid N2 and O2 coming out. Basically, this is a process that's proposed to be efficient in terms of liquefaction and regasification, transportation, and bringing back N2 and O2, and the entire life cycle in some sense, which is shown here. So methodological framework applied to estimate the potential of solid air hydrogen liquefaction. You can start here in SAHL description. So H2 regasification and liquefaction. So you have obviously liquefaction, transportation, regasification, solid air loading and unloading of the ship, transportation modes of integration, SAHL operation description, feeding into H2, N2 and O2 enthalpy, so you can track the energy conservation estimates. Coefficient of performance is computed, and volume and mass restrictions are considered for energy conservation estimates, and then you compare between N2 and O2 and air to see which one is the best. As we already said, O2 is actually better, but it can have risks in terms of transportation danger, so N2 that way is a compromise. So you have compressed H2 versus solid air hydrogen liquefaction. So there basically hydrogen economy is being compared between transporting compressed H2 versus this approach of solid air hydrogen liquefaction process, and this is the SHL global potential that's reported here. So they even propose a possible location for the liquid hydrogen production plant in the northeast of Brazil. In here is a top view with liquid hydrogen production plant LH2PP, offshore wind power plant to supply some of the energy needed for cooling, liquefaction, and so on, and national grid substation to distribute the hydrogen, and then there is a transmission line shown between them as well. In the vertical section down to about a kilometer or so, you have the substation. So the transmission length here is seen as order 20 kilometers, and with depth the water's cool, so you have 3 degrees C, so this is kind of an attempt to use a natural cooling potential. So pipeline length here is 10 kilometers and depth of about a kilometer to the LH2 tanker, so you want to transport it by ship. And there is the liquid hydrogen production plant, and you have offshore wind power, depth of 10 meters, transmission lines at 60 gigahertz, and so on. So this is just a kind of a possible location with its design suggested in this way. To make it also green hydrogen, you need to use obviously renewable energy for production, as we've discussed before. So very brief, but let's read the conclusions. The paper has presented a proposal to solidify air in the regasification process of H2 to recycle the cold temperatures in the liquid H2, so that's the energy recovery or the recovery of the heat that's released. Thus reduce the energy consumption and costs of H2 liquefaction. This regenerative solution has shown the potential to reduce the energy required to liquefy H2 is 25.4% using solid nitrogen and 27.3% using solid oxygen. Solid nitrogen occupies 44.5% of the volume of the liquid H2. Solid oxygen occupies 35.4%. So there is obvious advantages but risks associated with them as well. Future work will be performed to develop a detailed description of the entire process chain to describe in more detail the heat recovered from the SAHL process. We propose not to use solid O2 in SAHL for the risk factors. This is because we propose that solidification process happens with the hydrogen entering in direct contact with liquid H2 within the ship's tank, which can cause an explosion. H2 is highly oxidizable, of course. For this, the O2 from air will have to be separated from N2 during the H2 regasification process, since it's the solid air hydrogen liquefaction. SAHL has the potential to become the best alternative to transport hydrogen between continents in the future H2 economy. So this is not at all about producing green hydrogen, but it is about transporting it. Okay, so it is assumed here that a liquid hydrogen production plant exists, and then you are working with this solid air liquefaction process and transportation, recovery of the energy from gasification, and transporting nitrogen back, and so on. Okay, so I thought it's cute enough to include it very briefly, and obviously I have skipped many details that you can follow up on your own if that's of interest to you. Okay.